Hello, my name's Fernando. I write a blog called All About Turbo, and I am in my lab. And this lab I also use for another project called Iron Age Audio Works with a good friend of mine, and I have a small boutique custom audio equipment shop. We basically design and manufacture equipment that you would use on a professional recording studio. Now, so it happens that the equipment that you use to test and diagnose audio equipment is the same that you use to do vibration diagnostics. After all, sound is just vibration. So what I have here in front of me is I have an oscilloscope and I have a source of noise or sound or vibration, which is this mechanical device called a wobulator. It's basically a plate that spins, and it's intentionally misaligned so it wobbles. And when you look at you monitor it with a probe, like you would a steam turbine or a compressor with a proximity probe. We're going to intentionally be able to see what the oscillation looks like, or what the vibration looks like. So I have the proximitor output voltage connected to a digital multimeter, and also connected to this oscilloscope. So to make things a little simpler, to simplify things, I inverted the polarity of the probe. The proximitor is going to spit out usually a negative voltage, but I flipped that around so that we're dealing with positive voltages. So the first thing about the proximitor is the output voltage is directly proportional to the distance, or the gap between the probe tip and the target. So here I am pushing the probe against the target, and you can see that the output voltage, it's 0.6 or 644 millivolts. We're basically on the ground. And that's what this line, this one line on channel 1, I'm intentionally setting to ground, which is basically showing me the ground reference or 0 volt reference on the instrument. And then I am turning DC coupling on the oscilloscope, which is basically the same as the multimeter. Every square is 2 volts, and you can see that the voltage, the smallest voltage I can get out of this probe when the probe is touching the metal, is 654 millivolts, which is pretty much that gap. Let's just say we're on the ground, there's no clearance. Now in reality, we don't set probes to touch against the shaft. We're going to back it up, and we usually use a gap voltage of 10 volts. That is at the middle of the working range of the probe. So I'm going to back my probe out till we have 10 volts. And the cool thing that you see is as I move it out, it's also moving on the oscilloscope because we're measuring the voltage. So at 3 divisions, we're basically at 6 volts. We're going to keep going up. We're going to keep going up till we get to 10. So we are there. We are basically at 10 volts. Let's pretend that this is a machine. We've set the probe at 10 volts. You can see this is the distance. Basically what my oscilloscope is showing is a 10 volt gap between the probe and the metal, and it's the same that we see on the multimeter. Now, when I turn the equipment on, the wobulator on, at first we're not going to notice much vibration because the probe is looking at an area of the target that doesn't have that much undulation. So I'm going to turn it on. This little motor is going to be spinning at 7,400 RPM. And we can see the line on the oscilloscope. It's dancing a little tiny bit, but not very much. We could say we're at cruising altitude, and we are basically smooth sailing. Now, when I move the probe to an area of the target where there's a lot of undulation on the surface, you're going to see that on the oscilloscope, I see something that looks like a sine wave. And that is basically the turbulence. And when you look at the digital multimeter, you can see that that voltage is essentially staying around 10 volts, but it's going a little higher than 10, it's going a little lower than 10. And you can see that it goes like 9.9 and then 1.1, and it's just going up and down. That is basically the turbulence that you're going to hear. And I was making that analogy to where you're measuring two things. You're measuring the I can move the probe. I'm going to move it a little higher. And you can see that I moved the probe to a gap voltage on the multimeter at around 12 volts. But my vibration signal is exactly the same. So I just separated the probe a little more, but I'm still looking at the same vibration amplitude as I was before. I can bring it back down. I'm going to bring it down to 8 volts. So my gap voltage is around 8 volts, and my vibration stays the same. Now when I look at the DC couple, we can see that I have 8 volts, so 1, 2, 3, 4, 5, 7. I'm going to make sure. So I have 2, 4, 6, 8. So the mean of that sine wave, it's at 8 volts. And if I move it back up to 10, I move the gap voltage up to 10. The vibration amplitude stays the same because the target is wobulating with the same highs and lows. And this is what I wanted to illustrate, that you can measure these two things with a proximity probe, the gap and also the vibration. Now let's pretend that